Alright, if I can get everyone's attention really quickly. Doing the table was only part of the goal. What I mostly wanted you to focus on was how would I find that common ratio, how would I find that common difference? Are there any questions about how we found those common differences and ratios? Hey guys, I need you all to stop. Just listen. Like, the table was good and it was useful, but there was something more that I wanted you to see out of this. First off, are there any questions about calculating that common difference or that common ratio? From what I've seen, we've been able to calculate it pretty okay at this point. Now, good. One detail I do want to point out is this. What is the first step that you would take in solving this equation for that common ratio? Divide by 300. I will say technically it's not a common ratio in this case, it's a common factor, because a common ratio is between sequential terms, yada yada yada, it's for a sequence. But that's not what I need to focus on. Right here, divide by 300. R to the 12th is equal to what?
1.05.
Why does that make sense? Look at the original problem. Why should it make sense?
That's the 5%.
He started at 100%, increased by 5%. So realistically, should it be a linear, right? So the question is, which rate is correct, right? Should it be linear or should it be exponential?
Exponential.
It is percentage, right?
Yes.
We see the fact that that percentage matches the common ratio, right? So we do want to notice exponential, but I do want you to think about this. If you were to fill out those tables, does the difference really matter at all?
No.
I want you to see right here, you can't really tell. This is actually a graph from Desmos. This isn't actually one graph, this is two different graphs. There's a linear function right here and an exponential for over a year, right? So that's one full year right here. Can you really tell the difference between those two different functions?
No.
How about now?
Yeah.
Just barely. Like, I had to zoom in really far to see that difference. So for that 1 year, does it matter? So you don't think it matters at all, does it?
Not really.
How about over 15 years?
Wow.
Does it matter? So like, legitimately though, do you want to end up here after 15 years or do you want to end up here?
Oh, fair.
That's a significant amount of extra money. Starting out at $300, he would end after 15 years with about $525 if he was going at a linear rate. If he's going at an exponential, he's looking at about $650. That's a good difference, right? So we want to make sure we understand, like, exponential versus linear matters. So one, I hope that we feel more comfortable calculating those additive rates of change and those multiplicative rates of change. Does that feel more comfortable for us? But two, does it matter? Like long term, does it matter which rate of change you're looking at?
No. Oh, yeah.
Long term it does. Short term didn't make a huge difference.
No.
No, but long term it made a big difference. What I'm going to ask you to do is I am going to ask you to attempt numbers 13 and 14. It is on the back of 2.6. So that 2.6 that you just did, numbers 13 and 14, they should look very familiar. The point right now is for you to actually try them so that when you come in class tomorrow, you can say, hey, Mr. Kinney, I got it, or hey, I have some questions. I need you to actually attempt it. If you're not ready to ask questions, I can't help you. Sounds good? 2 problems, we can do it? Yeah?
Yeah.
All right, let's get our 2 problems done tonight. I want all of us to get hundreds. And McKay, can you let Gavin know the homework?
Yeah.
Okay? Dang, I totally forgot to give them 2 extra minutes to set their phone. I'm going to regret that tomorrow. Like I already know.
Yeah.
Yeah, probably.
You never know.
No, I know. I'm going to regret that.
Maybe what?